Okay, Mr. Camden, we're live for the first ever jog pod. How you feeling?
A little bit apprehensive about this, Mr. Unite, but I'm looking forward to trying to get as much information over in the next actual 15 minutes in order to be able to help all of our pupils to be able to do well in this particular unit. So let's start off then. We're going to take a whistle stop actual tour around these actual two revision sheets. Okay, so we're going to zoom in and we are going to start off on the global pattern of air circulation. Mr. Unite, what do you think about this here?
Okay, so some people find this a little bit complicated, but there's a really nice, simple way that we can break this down. So as you can see, the key information you need is there in terms of the location where they are. So in terms of the Hadley cell, we're going to find that both either side of the equator. So you can sort of see it there. I don't know if you can sort of point your arrow towards where the Hadley cells are, sir.
I'm doing that right now.
Directly, that's right. Directly over sort of the continent of Africa, okay? And that is our largest cell that we will find there, okay? So what we can start to think about is the sort of climate zones that we start to find within them, and that's going to feed into the box that we're going to look at just in a minute, okay? So that's our Hadley cell. Our feral cell we find sort of further up, sort of in the middle of these three cells. And what's easy to remember about that is if you ever hear about a phrase like a feral cat, okay, anything about wild animals and things like that, it's where we find sort of our wet and windy weather. So if you think about that, that's probably us. So as you can see, we're pretty much in line with the feral cell, okay, which explains some of our weather. And then obviously we've got the polar cells. As you know, we've got the Arctic and Antarctica at both sort of ends of the Earth, and that is where we see the feral cell. And then that leads on to our climate zones and what we find within those cells in terms of the climate.
Now, I just want to add here, so that I think this is like our kind of air conditioning actual unit up on for the whole world. Because if all this warm air around the middle of the Earth, the equator, if that air didn't actually move, it would be actually so super hot that obviously nothing would be able to survive there. And also, upon the polar regions, it would be so actually cold that obviously even less life would take place there. So all these different actual cells almost work like individual cogs in order to be able to move this cool air around this area and then better move all the warm area around.
Yeah,
brilliant. So onto climate zones. I like these as the kind of literally stripes, aren't they? Across the world here. Are you there, Mr. Unite? Are you there with us?
Yeah, no, I thought you were in flow there.
Oh,
so yeah.
Sorry. So in our actual tropical climate, all right, it's in between the Tropic of Cancer and the Tropic of Capricorn. Now, I always remember that it's alphabetical on for me. So go CAN actually becomes actually first rather than CAP up on for Capricorn. So
I got corns grow on your feet. So Tropic of Capricorn, point down to your feet.
Right.
There.
Two words. Yeah. I haven't got any corns on my feet though, sir.
No,
so we are in this actual the temperate actual climate, and as you said before, it's not too hot, it's not too cold, and things are able to grow and actually survive there. They don't have to adapt too much, do they?
Yep.
No, which is good, and often we would get actually more actual rainfall, all right, in these areas here. Okay, so all of the feral cell to help us, to be able to move this wind and all this moisture in the air around. What do you think about the polar climate, sir?
Well, really nice, simple. So you hopefully will remember from your lessons, they're very dry. Okay, Antarctica referred to as a desert because remember, desert's not to do with temperature; it's to do with the amount of rainfall. So here, if you think back to the diagram, you can see that there is sinking air, which brings dry, icy, and strong winds. Okay, so really nice and simple. Sort of then around that, so we've got our temperate and our polar. We also have another unit in your sustaining ecosystems that you looked at, where we looked at tropical rainforest. So hopefully you'll remember that we have high temperatures and we have high amounts of rainfall again. So we've got low pressure allowing air to rise, which we're going to talk about in a minute about low pressure. So we can start to see that coming in, but also because of the position around sort of between the tropics, it gets the full whack of the sun in terms of solar radiation, the concentration on it. Okay. In terms of the desert, well, again, we have obviously that high temperature, okay, 30 degrees north and south. Quite often people think we get our deserts along the equator itself, which isn't true. It's north and south of them. And that is where we see dry air, okay, and that is then more dense. Okay, so we start to find here that we get the high temperature still, but we don't get any rainfall. So obviously you think about places like the Sahara, Libya is the one example that's given for you there as well. So really this starts to link together to our high and low pressure, which we're going to move on to next. Mr. Cannon, high and low pressure.
Yeah, I always link this up onto the wind, you know, and if there's a lot of air particles and they're all condensed and they're all rattling around each other, all they want to do is just get some space, you know, and just be able to chill out. So all the air particles always look up on to be able to move up on from areas of actual high pressure down to low pressure, you know. So that's where we get our wind from. On the low pressure, we can be able to see here that it's actually caused by hot air rising, and we get more stormy, type of cloudy weather. And we get opposite when we go up onto areas of actual high pressure. Okay, it's usually actually caused by the cool air actually sinking, because what usually happens is that where we have all this sort of cold air, it sinks as obviously just United said there, because it's denser. Okay, right, that's low pressure for me, sir. Oh, what different types of winds? We've got actual wind, haven't we, that actually brings us all of our actual weather. Where does it come from, sir? Does it come from up near Norway?
Nice. Okay. Well, so we've got three on here. We've got the katabatic, we've got the trade winds, which some people have heard, and we've got the jet streams. Okay, so katabatic we've got here are winds that carry air from the high ground down a slope due to gravity. So if we think about Antarctica there, people often forget that actually it is obviously a continent. It's got land mass on it. It's got lots of mountains, sort of high areas there, okay, which will help to create that sort of wind. If we think back to the Hadley cell, Ferrel cell, etc., in terms of the global atmosphere circulation, we start to see that there are those areas that Mr. Canny was talking about, where we've got that movement, sort of like an air conditioning unit. So we've obviously got the winds that move from that high pressure belt to that low pressure. And they're moving along the surface. So it's a type of surface wind. The jet stream is slightly different. These are winds that are high in the atmosphere, so not necessarily on the ground like our sort of trade winds necessarily, and they travel at speeds of about 225 kilometers. So that all helps to move all of that different weather and climate sort of around on our Earth as well. But all of the things we've talked about so far all link back to that one diagram we looked at the top. So if you want to just scroll up to the top for me very quickly. And as we'll be able to see on it, okay, if you get your own diagram of like the Hadley cells and things like that, you can obviously see that like convection cells, okay, they rotate. We've got like, if we look at the Hadley cells in the center, that red line is showing that that wind is trying to move to that center part, okay? And then we've got obviously the cool winds that are being pushed along from the top, and then they are sinking down at those other areas as well. Okay, so we can start to see where that high and low pressure matches up to that diagram of the global atmospheric circulation model.
So that's what we're talking about
you.
On the jet streams, I always think, you know, if you go into America or something like that, you know, and I bet takes about 9 hours one way if you're going to Miami, and then on the way back it could take maybe 10 hours, and you're thinking, what is actually causing that? Is that just because the engine doesn't want to go as fast? But
no, that's true. I remember asking that question when I went to Canada when I was about 14. Nice little link.
Dreams, yeah, brilliant. So when we go to precipitation, people say, is it all right if I just put rain? But obviously we get different types of wet stuff come from the sky, don't we? So it's everything, you know. So it's snow, it's when we get kind of hail as well. So always look to talk about it being precipitation rather than just rainfall.
Yeah, which is what we'll see on a climate graph as well. So when you look at your climate graph, it says precipitation, not necessarily always rainfall on there as well.
Yeah, and we should actually be able to talk about actually how that actually happens. So obviously, all the water vapor gets evaporated, especially when it's hotter, and it goes up into the clouds. As it gets higher, it begins up onto cool down, and then all the water vapor actually condenses to form an actual cloud. And then when it gets really, really heavy, then it just comes back down to earth as precipitation. Right, we're going to take a bit of a wander back up here, up onto where we're talking about drought. Where do we get most of our droughts, Mr. Unite? What type of areas? I think you may have hit on it earlier.
Well, you mean about our deserts, sir, and areas that we have in particular, areas of high pressure, because in those areas we don't have the ability, like you said, about that precipitation that wants to rise through evaporation, isn't allowed to rise, so it doesn't create clouds, sir.
Right. Okay. So if there's no water vapor, then there's obviously going to be no actual clouds, and there's going to be no precipitation, is there?
No, indeed. And, you can see on there, you start to see your trade winds, your warm and dry subside, so that's starting to drop down. Yeah, so we've got the El Niño La Niña, sir.
Yeah. A bit of a difference here, and it's all down to these actual trade winds. If they begin to speed up, then even more of this warmer actual water and air moves towards Indonesia. And then if you get more actual heat over here, what are you going to get, sir?
Sorry, sir. I lost you for a second there.
Did you seriously?
Yeah.
I was in mid-flow there. So
my connection's gone a bit dodgy.
I thought it was your knowledge. Right. So here we have, warm water here, and all these winds, as it gets stronger, pushes all the warmer water more west. Okay. And we get actually hotter areas around here, which are going to lead up onto what type of conditions, sir? Who's lost you? No. Right. I'm flying solo here, guys. Right. So as we can see, we get actually hotter weather here, okay, which obviously causes lots of drought in Australia, Indonesia, and this and here. But then we get more evaporation. So then as this type of the moisture in the air rises up, okay, it will then begin to fall down, all right, and we get more rainfall in here. But if these actual trade winds begin to slow, we end up coming into an El Nino, which only happens every 2 to 7 years, okay? And this begins to be able to reverse the cycle, okay, which is what can happen here. So all this warm water gets spread in the middle, and you end up with a double cycle, okay? And that's when we have more stormier conditions in the middle of the ocean here, all right? And we can be able to see that we have hotter areas around here, right? So we are going to go back down to a little bit of extreme weather for different types of examples around the world, okay? Wellington, which is often known as a windy city, it's obviously very windy around here because it goes up to 250 kilometers an hour. So that's an example you can be able to use here. In Chile, all these mountain ranges here actually causes rain, okay? But it goes a long way down here, so it's exceptionally wet down here, okay? Puerto Lopez, okay, of equator here, temperatures, okay, a rapid condensation and heavy rainfall. India, see a lot of rain each year, 11 meters per year. So if I'm 2 meters actually tall here, there's going to be over 5 times the height of me each year. Wow.
How tall are you, sir?
Sorry, sir?
How tall are you?
I'm 201.
201.
Officially a giant. But let's move back to this, sir, because I don't know if you've been away. Have you been for a coffee or something?
I embarrassingly got called, so I had to try and sneak away.
All right, thanks for that. Thanks for team player.
Right.
Right. So we've got these actual tropical storms. All right. Now over here we have this wonderful flow chart here of a tropical storm, and you can just be able to see here that it's got this magic number of 27. So I'm going to leave you on this one, sir, because I know that this is an area that you did exceptionally well in at university.
So excellent, yeah. So essentially, what we want to be thinking about for our tropical storms is there are a couple of key things that we need for them to form. Okay, so we need them to form obviously between the tropics, hence the name, but that links back to our global atmospheric circulation because we want them to be in areas where we've got low pressure because it's all about evaporation and heavy, intense rates of evaporation because that's what provides the energy for our storm. So Mr. Canny was talking about with our sort of low pressure, that rising temperature because it's 27 degrees creates a real big sort of rising sort of plume, if you so wish, of evaporation. Okay, so if you sort of scroll through these sort of things, I'm going to sort of try and summarize a little bit, not read word for word, but on the knowledge organizer, there's 6 stages for you. Okay, so we've got nice warm oceans. This is why at certain times of the year when we come back in sort of September and October time, when we teach this topic, it's often really the case that we suddenly go, oh, look, have you seen in the news? Because for places like America, the USA, etc., they all have sort of seasons where the oceans have become nice and warm, and at 27 degrees with that low pressure is the key things that we need. Okay,
Often that's in and around. Sorry, sir. I just want to try to give a little bit of an example of the locations there. So that's usually off a coast near Florida. Okay, so it's actually quite far down on the east coast of America.
Excellent, yeah, and obviously we've got other different locations, and so obviously there might be like Cyclone Nargis, which hit India. Those of you that were watching the Rugby World Cup, obviously there was some out in Japan during that particular time as well. Okay, and as I'm sure you know, obviously the Earth does spin. Okay, we call that the Coriolis effect, and that's really important because what we obviously start to happen is obviously we have that high rates of evaporation. We've got that low pressure, which creates storms. But because the Earth is spinning, if there are multiple storms, they start to form and make one larger storm, which is what the tropical storm is. It's a significantly larger storm than those that you might imagine before, okay? And then once eventually that storm has generated enough energy through that evaporation, it continues to spin. And then like a 74 miles down here on stage 4, that's when we actually see that hurricane being born because it's big enough for it to be what are classed as a tropical storm. But once we get inside, we have sort of, again, like a bit of a sinking, a bit like the air conditioning unit that we talked about for the global atmospheric circulation, where we've got sinking air in the center of the storm, which is why when you look at a diagram and you see the eye, that is the area of really calm and clear conditions. But then on the outside of that, you have what's called the eye wall, which is the most violent part of the tropical storm. And then we've sort of got the wider sort of bits out of that, which is sort of the, what are called the, oh God, I've had a mind blank, sir. We've got the clouds.
Let me talk about in the wall of the hurricane. Yeah, often that's where you better see it in old movies where you see pictures of cows and cars, you know, going around in the wall of the storm. Okay, but I think Mr. Unite, have you got your word now?
Yeah, they're called spiral bands.
Spiral bands. Is that a bit like the? Go on.
Yeah, so we've got obviously our eye in the center, which is the calm part. Then the most violent part, where we've got really high winds, really heavy thunder and lightning and rainfall, etc. And obviously, as we go, we imagine that the tropical storm does start to thin, and we start to see like wispy clouds, and that's where we might see less worse conditions. Okay, so we're starting to think about lower levels of rainfall, maybe not necessarily thunder and lightning, but heavy rainfall and moderate winds. Okay, but obviously, as it moves, the eye will pass over. So actually, most of the areas that have the eye will eventually have been hit by the eye wall and the severe sort of storms and weathers that brings. But what it means, though, is obviously the source of all this power is the ocean. So that's why you often hear terms they talk about landfall and how when tropical storms make landfall, they start to die out or lose their strength. And that's simply because there's a reduction in the amount of energy with that evaporation, which is the key sort of fuel for it. Along with that, water has less friction. So as it starts to go over land, more friction is created, which also helps to cause it to slow down. Okay, but that's a really quick summary of tropical storms.
So if it actually travelled actual further over warm water, it would get even more power, wouldn't it? So if it's
more time it spends, the bigger it grows. Yeah, like that.
Brilliant. Okay. We've got a little example here, one of the individual case studies. I know that this is actually quite obvious here, but when it gets really hot, and it's been getting hotter and hotter and hotter over recent actual years, but one of the of examples that we got here is a UK heat wave, and usually it's younger people and the older people that are actually more vulnerable. Okay, so people have to try better manage it, but it also had negative effects as well, and they are there. But obviously, the most important one, that sports day was cancelled. Would you believe? Because it was so hot and we couldn't get enough actual water out for people to be able to keep themselves hydrated. And as we all know, hydration is key. Right, let's look at these areas. I'm not going to go up onto too far up onto this now, but we can remember that this was a super typhoon. Where do we get? I get confused sometimes in between what's an actual typhoon, what's an actual hurricane, what's a tornado. But I always would say, if you don't know what it's actually called, call it a tropical storm. Would you?
Yeah, I would say. Yeah, they do have specific names. So Indian Ocean is cyclones. Typhoon is sort of the we call it sort of the Eastern Pacific, because obviously for the US they all call them hurricanes, but technically the Pacific Ocean is to do with typhoons. But the west coast of the US obviously would be called something different. So to make it easier, on the west coast of the USA and the east coast they both call them hurricanes, rather than calling one side hurricane and one side typhoon.
Brilliant. Right. On the case study there, there's going to be a whole actual individual pod up on for those ones there. So let's not worry about that there. Right. That has come to the first ending of the first actual session for Global Hazards page 1. There will be page 2 coming out soon. Thanks for being with us, and I hope you've got some good questions. If you have, ask your geography teacher. Thanks, Mr. Unite.
Yeah, thank you for your time. Thank you very much, Ms. Cannon, for your help.
Bye-bye.